Well, good evening, everyone, and welcome to the U.S. Geological Survey's monthly lecture series. My name is Bill Ellsworth, and I'll be emceeing today's program. Thank you all for coming tonight. I hope you didn't have too terrible a time getting here, because I know the traffic today is extremely bad on the roads. So thank you all for being here promptly and on time. I want to mention that next month, on September 24th, we'll have the next lecture in our public lecture series. It'll be given by Kurt Strelazzi, and his title is Coral Reefs, Climate Change, and Atoll Sustainability. I think being on a coral atoll sounds good to me tonight. So anyway, we're very pleased to see all of you here tonight, and to be here to hear about a topic that has become increasingly important in recent years. And Justin Rubenstein, our speaker, his title, as you have undoubtedly learned by now, is Yes, Humans Really Are Causing Earthquakes. So let me give you a little bit of background about Justin and why he can make such a bold statement. So Justin is a seismologist here in the Earthquake Science Center of the U.S. Geological Survey, and he leads our research group that is working on earthquakes that are caused by fluid injection. So we'll be hearing a lot about fluid injection earthquakes tonight. His work focuses on the ongoing surge of activity in the central United States and its relationship to oil and gas operations. Among the things that he's doing, he's developing methods to forecast where and when these earthquakes will occur in the future and understand them in ways that we can learn how to reduce the hazard that they pose. His career accomplishments include many things, a broad range of topics in earthquake research, including earthquake forecasting, studying earthquake ground motions, the shaking that comes with repeating earthquakes, and the still mysterious rumblings that we call tectonic tremor. Justin received his bachelor's degree from UCLA and his master's and PhD at Stanford University, and he was a Mendenhall postdoctoral fellow with the USGS before becoming a permanent part of the USGS Earthquake Science Center. And he tells me that while he's excited to work on such a socially important topic, he never expected that he'd be spending so much time talking to reporters or studying parts of the central United States where humans really are causing earthquakes. So please join me in welcoming tonight's speaker, Justin Rubenstein.
Thanks, Bill. So as you can see with the title, I'm pretty unequivocal here. We really are causing earthquakes. And we've just got a couple of photos here. On the right-hand side is a damaged tower from Benedictine Hall at St. Gregory's University in Shawnee, Oklahoma. This was damaged in a magnitude 5.6 earthquake near Prague in 2011. And so this is some damage actually from an induced earthquake induced by wastewater injection in central Oklahoma. On the left-hand side, it's a Photoshop that I thought was pretty funny, and I like to show this. You know, when we think of Oklahoma, we think of tornadoes, but now they're actually the earthquake capital of the continental U.S. as well. They're ahead of us here in California, so somebody dubbed them home of the Quake-nado. And so through this talk, I'm going to be sharing a lot of my own research, but also the research of many, many others. We've got a strong group here in Menlo Park, as well as Pasadena and Golden, Colorado, that are all working on this topic. There's also a lot of work being done by other government scientists, university scientists, et cetera. And so I'll be sharing a lot of different research from different groups. And so, yes, humans really are causing earthquakes, but I want to caution you, it's not in the way you think. It is not Lex Luthor or Max Zorin causing these earthquakes in A View to a Kill or the original Superman movie. Strangely enough, both of these guys, the way they wanted to cause earthquakes was by placing bombs into the San Andreas Fault, causing a large earthquake. Actually, Max Zorin, in A View to a Kill, which is the James Bond movie, he actually planned to put bombs underneath Crystal Springs Reservoir right here and flood the fault, causing the earthquake, which is actually, flooding the fault is actually very similar to what is occurring in Oklahoma, for example. So, they were a few years ahead of their time, or at least about 30. But really what I mean by not in the way you think is I suspect most people are thinking these earthquakes are induced by hydraulic fracturing. And hydraulic fracturing really is not responsible for the vast majority of these earthquakes. Hydraulic fracturing is indeed responsible for a small percentage, but it's actually a different process used by the oil and gas companies called wastewater disposal or saltwater disposal that we believe is responsible for the majority of these earthquakes. So I will ask you to suspend your disbelief and hear what I have to say in the explanation as to why wastewater disposal is really the important factor and not hydraulic fracturing. But first, I want to tell you a little bit about induced earthquakes. This is not a new phenomenon at all. The induced earthquakes were discovered 120 years ago. These were the first known man-made earthquakes felt in Johannesburg in 1894. The Witwatersrand goldfield just to the south of Johannesburg was very active, very rich area. And you can see in these photos, some nice photos from the late 1890s of this very primitive mining operation. They were using what's known as room and pillar mining. And basically collapses in these mines effectively turned into earthquakes. You were able to feel them in Johannesburg. And so these are the first known what we call induced earthquakes. And so induced is the term that those of us in seismology, those of us in earthquake science, use to describe earthquakes caused by human activities. And shortly thereafter, a seismological laboratory in Bochum, Germany, was started in 1908 to actually study this exact kind of phenomena of these man-made earthquakes. So it really spawned a lot of work pretty quickly. And shortly thereafter, in 1920, the first seismological laboratory where they were actually deploying seismometers to study induced earthquakes, that happened in 1920 in the Silesia coal basin. So as you can see, this is a very long-standing phenomenon, something that we've been trying to understand for a very, very long time. Now, mining is not the only source of these kinds of earthquakes. There's many other human-made earthquakes or induced earthquakes. And some of the other historical induced earthquakes were oil production-related earthquakes. So this is a photo of Goose Creek, Texas. This is outside of Houston, about half an hour to the east. And you can see there's just oil derricks everywhere. They're pulling out oil like nobody's business. And so the extraction of the oil and gas in this area basically created voids. And by changing the mass that is in the earth, they basically changed the forces that are on these faults, in this case, making earthquakes more likely. And so this is just a second example of known induced earthquakes that are now 90 years old. So this was the second sort of way that we were able to identify human-made earthquakes. And the last historical kind of human-made earthquakes was from the filling of Lake Mead in 1935. This is actually a recent photo showing you how low the levels are in Lake Mead. But when Lake Mead was filled in 1935, they started feeling earthquakes in the vicinity. And so what they were able to conclude is by pouring in all of this extra water, they're adding a whole lot of mass. And so that's going to be pressing down on faults below it, and that can make earthquakes more likely again. And so these are just three historic examples of human-made earthquakes. They were a long time ago. And so this is not a new phenomenon. While we're really thinking about it much more in the past 5 or 10 years, this is something that's been going on for a very long time. Now, seismologists use a number of different characteristics to try to understand or identify whether an earthquake is induced or if it is natural. Now, first, we even are brought to the question as to whether earthquakes are induced is if we see a change in earthquake behavior, if we suddenly see an increase in the earthquake rate. Now, this is going to be very easy to do in places like Oklahoma or Kansas, where there really is very little or no background seismicity. Doing this, say, here in California, where we have lots of seismicity, is a much more challenging problem. So this is partly why we're spending a lot of our time studying these earthquakes in quiet areas. Now, the way we identify the induced earthquakes, we use basically 3 different criteria as sort of a starter to bring us into really thinking about this. First, are these earthquakes that we're seeing, are they close to the source of the stress? Are they close to the reservoir, for example? And in the case of Lake Mead, these earthquakes were pretty much right underneath the reservoir. The next question is, are these earthquakes happening shortly after this stress change occurred? In the case of Lake Mead, again, shortly after they started filling the reservoir, they started seeing earthquakes. So we're now seeing a connection both in space and time. And the last criterion that we use is, are these earthquakes close to the surface? Human activities are typically going to be at or very close to the surface, so the stress changes that we are imparting are going to be strongest at the surface. And so we'd expect any earthquakes that are generated by these activities are going to be occurring close to where these activities are, so near the surface. Now, this is all well and good. These are really easy to follow criteria, but these are not hard and fast rules. I can show you examples of induced earthquakes that violate every single one of these rules, and I can probably find you an earthquake sequence that violates all three of these rules at once. So it's not quite so easy. We can't just use this as a yes or no based list. So why are induced earthquakes suddenly such an issue? And I think a lot of you have probably seen plots like this before. What we're looking at is a cumulative count of earthquakes since 1973. And you can see from 1973 to about 2009, the earthquake rate is pretty much constant. We're looking at magnitude 3 and larger earthquakes in the central United States. And the earthquake rate is somewhere on the order of 20 or 25 magnitude 3s per year. Pretty low, pretty quiet, not a whole lot happening. But then you can see in about 2009, this starts to take a turn, starts turning upward. We're starting to see more earthquakes. 2012, it sort of levels off a little bit. And then 2013, 2014, and 2015, it's really flying off the handle. We've now seen more earthquakes just in the past 6.5 years than we saw in the preceding 35. So something very, very different is going on. And it's not just that we're seeing a lot of magnitude 3 earthquakes. Magnitude 3 earthquakes, we all know here in California, really, it's more an annoyance than it is a danger. But it's not just magnitude 3 earthquakes that we're seeing. We're starting to see damaging earthquakes. As I mentioned, the magnitude 5.6 Prague earthquake in Oklahoma, and yes, that is actually how they say it in Oklahoma, this caused damage on 14 different buildings in the area. Like that photo I showed you of Benedictine Hall as well. And so you can see this is an unreinforced masonry building, a brick building. These are particularly susceptible to damage in earthquakes. And so you can see there's pretty significant damage from what we would consider a fairly small earthquake or a moderate earthquake here in California. Then you look at the magnitude 5.3 Trinidad, Colorado earthquake, also in 2011. And you can see, again, another unreinforced masonry building, a brick building, facing a pretty significant amount of damage. And there's a theme here. Brick buildings are particularly susceptible to damage in earthquakes. If you think back to the earthquake just last year in Napa, most of the buildings that were damaged were, again, brick buildings. And so this is really something that we need to be thinking about when we're thinking about earthquakes in the central United States. They're not really building to the same earthquake codes that we are here in California. And so that potentially makes what we would consider not a very significant earthquake would start to be a more significant earthquake in these places. So the earthquake behavior, it's not just a change in the earthquake rate. It's not just that we're seeing way more earthquakes, but the distribution of earthquakes has changed dramatically. So this is what the earthquakes look like from 1973 to 2008, and it's pretty scattershot. You can see there's sort of a cluster of seismicity here, there's a cluster of seismicity here, and there's some scattershot sort of along the Rocky Mountain area, but there's not really a strong clustering of seismicity. But if you look at the last 6.5 years, you see that most of the seismicity is really concentrated here in central Oklahoma and southern Kansas, a few different spots in Texas, and the Raton Basin, and here down near the Mount Carmel earthquake in Illinois. But it's very, very different. It's not this sort of scattershot, chicken pox sort of behavior. It's much, much more limited. Yet, the earthquake rates are very, very different. So this is just the 1974 to 2008 seismicity. There were 855 magnitude 3 earthquakes during this time period, so an average of 24 earthquakes a year. Now, the past 6.5 years, we've seen a full 1,000 more earthquakes in this same area. So in a period of 6.5 years, we saw 1,000 more earthquakes than we saw in a period of 35 years. So we've increased our earthquake rate from 24 magnitude 3 earthquakes per year to over 277 earthquakes per year. So we're seeing not only an increase in earthquake rate, but a significant change in the seismicity patterns, and the seismicity is very, very clustered. And the earthquake rate changes are really limited to a few small areas. And I'm going to show you this just sort of by subtracting out these individual areas sort of one by one. So again, we're looking at the earthquake map from 2009 to last week. And this is just a count of the earthquakes. And so we're just going to subtract out individual areas. First, we'll take out Oklahoma and Kansas. So circle those and subtract those out. And, well, you're already much closer to where we started. Then we can subtract out central Arkansas. This is the Guy Greenbrier earthquake sequence in 2010 and 2011. And we're getting even closer. We can then subtract out the seismicity in the Raton Basin. This is an earthquake sequence that actually began in 2001. And you can see that we're pretty much flat. We can subtract out a few more in Texas as well as Colorado. And now we're really back to the background rate. Simply by removing seismicity in just a handful of areas, we're now back to the background rate. And so this is really showing us that the seismicity change in behavior is really limited to a few different areas. And all of these areas are areas of intense oil and gas activity. So I think we can pretty fairly make the argument now that this earthquake rate change is due to these nodding donkeys and energy extraction activities. Now, we need to go through the energy extraction activities or the energy extraction techniques because there's a lot of different ones that can all cause earthquakes. And I'm going to go through 4 different techniques, and then we'll focus in on hydraulic fracturing and wastewater injection because those are really going to be the 2 biggest players here. So hydraulic fracturing, well, this is just an example of what a frac job looks like. It's a pretty intense sort of operation. There's pipes going every which way. It's really quite impressive. And the largest earthquake that's been induced by hydraulic fracturing actually happened just a week or 10 days ago in Alberta. It was a magnitude 4.6. Prior to that, it was a 4.4. And really, we're seeing all of the biggest frac-induced earthquakes occurring in Alberta or British Columbia. The largest frac-induced earthquake we've seen in the United States is somewhere in the mid-magnitude 3s. And this is something that we're trying to understand, is what is different between earthquakes, hydraulic fracturing-induced earthquakes here and in Canada. Now, the second way that humans have induced earthquakes from oil and gas activities is production. And so these are the nodding donkeys that you see here, that you see on the side of the road. These are pulling out oil or gas. And production, by virtue of pulling out the fluids, you're changing your conditions, and that can cause earthquakes. And the largest earthquakes we believe to be related to production were a series of 2 magnitude 7 earthquakes in the late 1970s, early 1980s in Uzbekistan. And this was a natural gas field. Both of these earthquakes were on the order of magnitude 7. Now, the other 2 techniques I want to mention are wastewater disposal. This is a picture of a wastewater well that I visited in Weld County, just north of Denver, a number of years ago. And it's not a particularly impressive piece of machinery, but this is putting down large volumes of water pretty much day and night. And the biggest earthquake we've seen so far was a magnitude 5.6. That was the Prague, Oklahoma earthquake in November of 2011. And the last sort of oil and gas related technique that we've seen to cause earthquakes is what's known as enhanced oil recovery. Now, in wastewater disposal, we're flushing water down into a different reservoir below where we're trying to extract oil and gas to try to sequester that water, to keep it away from anything that's going on. Enhanced oil recovery is a different technique where they're actually flushing water into the formation that bears the oil or bears the gas. And they're trying to actually push the remaining oil towards their remaining production wells so they can improve the oil recovery. And so typically, we don't expect enhanced oil recovery to cause earthquakes because you're more or less maintaining a fluid balance or a fluid pressure balance. And so you really shouldn't see a whole lot of earthquakes. But we've still seen the largest earthquake is about a magnitude 4.5. So I briefly want to go through how these operations cause earthquakes. And there's 2 main different ways. One is a fluid pressure way, and one is a change in solid stress or mass. And so I'll start with this one because this is really the main way that we think of for causing these larger earthquakes, and that's a fluid pressure effect. So this is our well right here, and you're going to be injecting fluids either through hydraulic fracturing, enhanced oil recovery, or wastewater disposal. And you're pumping this water in. And most of the time, frankly, nothing happens. The water goes in, and you never see it again. But on occasion, there's a hydraulic connection. There's a way for the water to get from this reservoir that you're injecting into a fault. And so as that water flows into the fault, it actually raises the fluid pressure in the fault. And so in some sense, it pries the fault apart, resisting the forces that are clamping it together. And so by prying it apart a little bit, there's less friction to resist slip, or less resistance to producing an earthquake. And so this is sort of how we imagine earthquakes being induced by fluid pressure. Is basically you're making it a little bit easier for an earthquake to fail, or an earthquake to happen. And if you're close to failure, you're probably going to get earthquakes. Now, an important thing to think about, though, is the fluid doesn't have to get all the way from the well to the fault. It is merely the fluid pressure. If you think about the brakes in your car, when you step on the brake pedal, it's not that the brake fluid goes all the way from your foot to the brakes on your car. It's just the compression that is going all the way there. It's just that fluid pressure. And so this way, the effects of a well can be felt much further than you might think. Now, the other way that oil and gas, and in fact pretty much all of the human-induced earthquakes can be caused, is through these solid stress changes or mass changes. By either adding volume, like in the case of filling a reservoir, or removing volume, like in the case of mining, you're changing the amount of mass, you're changing the amount of pressure on faults that are either to the side or below this. And so this is, by changing the stress conditions, you can make earthquakes more likely. So now I want to spend a little bit more time talking about hydraulic fracturing and wastewater disposal, and I'll explain to you why wastewater disposal is more important in this equation in the United States. Now, first off, hydraulic fracturing is not new. While it's only recently gotten in the news, it was invented almost 70 years ago. And it's a technique that, in some sense, they're trying to make earthquakes. They're injecting fluids at very high pressure, trying to break up the rocks. But the earthquakes that they're making, this breaking up rocks is making an earthquake, but they're making incredibly small earthquakes. These earthquakes are magnitude -2 to maybe magnitude 1. These are earthquakes that you're never going to feel on the surface. They're just too small. Now, these operations are going to be very, very short duration, typically on the order of hours. In a really big frac job, you're looking at a few days. Injection volumes are on the order of 60,000 barrels per well. For those of you that are beer drinkers, 1 barrel is 2 kegs. So you're going to be busy for a few months at the very least drinking that. For those of you that are not beer drinkers, that's 42 gallons in an individual barrel. And a very important point to take away from this is that there's no such thing as a hydraulic fracturing well. This is a production well. This is a well that you want to extract the oil and gas from. So you flush in this water to break up the rock, and you pull it out, and then you start sucking out oil and gas because that's really what they're in the business for. So these are just some more photos of frac sites. Again, this is an incredibly complicated situation, pipes going everywhere. I've been to a couple of frac sites, and it really is quite an impressive feat. And this is just a photo of some water trucks lined up at an individual frac site that I visited. And there's probably 100 or 200 of these trucks that are all filled with fresh water just for one individual well. It's a really impressive operation. So I'd also like to show you sort of a cartoon of what is actually happening in an individual frac. So right now we're looking at our well right here. It's going straight down. And sort of the shaded area is showing you where this well, before fracking, where you can access oil. And so you can see that there's not a lot of connections in these cracks that might hold oil to our actual well. So this isn't going to be a very valuable well because you can't contact a whole lot of oil, so you're not going to be able to pull it in. Now, by flushing in this frac fluid at high pressure, you're breaking up rocks and you're allowing there to be more connections to you're able to access a larger volume of rock that's holding the oil or gas. And so now you're able to access all of this area. And so this is really why they're doing the fracs. Another important point is that fracking is occurring very deep. The oil-bearing formations are often, thousands of feet below the surface. And so this is just a cartoon showing you exactly that. Here's our well pad, and they've drilled down through many different formations. And they actually, in this cartoon, they've actually turned the well so it stays within this formation, which is probably bearing the oil or gas. And so they've fracked it in many different places to maximize the amount of oil or gas that they're able to pull out. So the other process that I want to talk about is wastewater disposal. And I've told you over and over that this is the process that's responsible for most of the earthquakes and all of the big earthquakes that we're seeing in the United States. But first, I probably should explain what wastewater is. Now, wastewater is just any fluid that is produced in the oil and gas process that can't be reused, it can't be cleaned, it needs to be disposed of. Now, frac fluids are going to be part of this waste fluid. Typically, oil and gas companies want to reuse frac fluid because it's primarily fresh water, and fresh water is expensive. So if they can reuse it, they will, but sometimes the frac fluid is too dirty, and they have to dispose of it in another way. But generally, the largest component of wastewater is what's known as produced water. Now, produced water is just water that's found in the same formations as oil and gas. So if we look at sort of this cutout of a hillside, you can see our well that's drilled down here. And here's our oil that's contained under our cap rock. And in the same formation, this oil reservoir, there's water. And this is salt water, and this is natural. This is expected because oil is basically produced from relict oceans. And so you're going to have salt water hanging out in the same place. And so when you pull out oil, you're going to be pulling out salt water as well. It's just not really an option because the oil and water are mixed together. Now, in some areas, and you're going to see produced water in basically every oil or gas well. It's just by virtue of there being oil, there will be salt water as well. Some wells that are fracked will have lots of produced water. Some wells that have not been fracked will have lots of produced water. So it's really, the fracking process is to some degree irrelevant as to whether or not there will be this produced water that needs to be disposed of. Now, in some areas, almost all of the wastewater is actually what's known as this produced water. In Oklahoma, there's an area known as the Hunt and Dewatering Formation that isn't even fracked at all. And so this is all of the water is going to be this produced water. So we've got all this produced water that's either frac fluid, all this wastewater that's either frac fluid or produced water. So what do we do with it? If you can't reuse it, if you can't clean it up and discharge it on the surface, the option that oil and gas companies have taken on is drilling an even deeper well. So they're going to drill this well below the production. This is our production formation. They drill it even below there into a sandstone or some other porous rock and start putting the water in there. And generally, no big deal. They put the water in, you never hear from it again. These wells typically operate for years, and they can be very, very large. Some of the largest injection wells are injecting over 1 million barrels a month. I've seen some areas where you've seen over 1 billion barrels injected over the lifetime of a number of the wells in the area. So far bigger than a hydraulic fracturing job. Now, in the United States, we've got about 35,000 of these wells that are active at the moment, but very, very few have been connected to earthquakes. And I just want to go back over how these kinds of wells and hydraulic fracturing is going to induce earthquakes. You're flushing this water down into this porous formation, and occasionally there's a way for fluid pressure to get transferred to the fault. The fluid gets into the fault, pries it open, making it a little bit easier to cause earthquakes. Now, let's go over why wastewater injection is more important than fracking when it comes to inducing earthquakes. Now, first off, wastewater disposal is a very long-term process. This is going to be something going on for years or even decades, whereas a frac job is going to be hours or maybe days. So your exposure time, the time when the amount of fluid you've got in affecting your stress conditions is much, much longer in a wastewater disposal scenario. And so that means the opportunity to produce an earthquake is over a much longer time period. So this, to me, implies that you're more likely to be inducing earthquakes through wastewater injection. Second, wastewater disposal is much higher volume than hydraulic fracturing. We see large wells injecting 1 million barrels a month. You can wind up with volumes up to 1 billion barrels from a few wells combined, whereas a frac job, you're looking at many orders of magnitude smaller than that, 5,000, 50,000, 100,000 barrels. So the magnitude of the stress changes, the effect, the strength of the effect of wastewater injection is much larger, and it's felt over a longer period of time than it is from hydraulic fracturing. And so this really shows you why we believe wastewater disposal to be the primary source of the induced earthquakes. And statistically, we also see this borne out. There's about 35,000 of these injection wells that we see, wastewater disposal wells that we see in the United States. And we've seen many, many felt earthquakes. And there's been at least 20 or so damaging earthquakes from wastewater disposal. Now, most of these damaging earthquakes, we're really only looking at cosmetic damage, very minor damage, but these again are fairly small events. But if we look at fracking, there's been over 1 million frack jobs in the United States, and very, very few felt earthquakes, and as far as I know, no damaging earthquakes. So despite the fact there are far more frack jobs, the amount of damage and the amount of felt earthquakes is far, far fewer, despite there being 10 or 20 times more operational wells. So from all this, we can really glean wastewater disposal is much more likely to induce earthquakes than hydraulic fracturing. Now, I'd like to walk you through the discovery of injection-induced earthquakes, and this happened in the 1960s. This is a photo of the Rocky Mountain Arsenal just outside of Denver, and this was a chemical weapons facility, and as you might expect, there's going to be some pretty nasty waste associated with this. So the Army drilled a deep well into crystalline basement and started flushing that waste away. And shortly after the injection started, people started feeling earthquakes. And it wasn't an instantaneous aha moment. Somebody didn't put it together immediately. It took a little bit of time. This was work done by people who preceded me here in Menlo Park, as well as our offices in Denver, as well as many other scientists in the Colorado area. But they were actually able to connect, these were the first people to connect fluid injection to inducing earthquakes. So what we're looking at is a span of 4 years from 1962 to 1965. This is just a count of earthquakes here. And this is just an amount of fluid that's been injected. And you can see that they track each other pretty nicely. You have a spike in earthquakes that's associated with a spike in injection, another spike in earthquakes followed by a spike in injection. They actually stopped injection for over a year, and you can see that the seismicity waned, but they turned the well back on, and the seismicity turned back on. So it's a pretty clear and convincing case that these earthquakes are being induced by this injection activity. Now, something important to take away from this is actually the largest earthquake that occurred that was induced by this injection actually happened over 1 year after they terminated injection. So it's not just as simple as turn off the well, the earthquakes go away. That often does happen, but it's not a silver bullet. You may wind up with a more complicated situation. So this is just a photo of some of the damage from the magnitude 4.9. So you can see, again, it's not major damage, but again, this area is not really constructed for earthquakes. And if we look here, this is a photo, this is an image in cross-section, so we're looking sort of sideways at the Earth. What you can see is this is the bottom of the well. This is a 5-kilometer ring, so about 3 miles. And all these dots are showing you earthquakes. And so this is 1967, a full year after injection is terminated. And all of the earthquakes are far away from the well. And this is really showing you what this problem is while there's no earthquakes right around the well, the pressure pulse caused by the injection has sort of dissipated away close to the well, but it's still traveled all the way out here. And so this is why we see the larger earthquakes later. And shortly thereafter, scientists here again in Menlo Park, as well as at the USGS office in Denver, somehow convinced Chevron to let them take over part of one of their fields. And so this is a photo of Jack Healy and Barry Raleigh, and John Bredehoft was the other major person working on this, and he probably was the one taking this photo. And they're sitting next to one of their injection wells. And so Chevron had a field in western Colorado called Rangeley, where they had been seeing lots of induced earthquakes. And so these guys managed to convince them, hey, we want to conduct an experiment. We want to understand what's causing these earthquakes. Will you let us take over this field for a year, 2 years? And like I said, amazingly, Chevron let them take it over. And so the first 6 months here, here we're looking at cross-section, here we're looking just at a map. They pumped the reservoir up. They injected lots and lots. And you can see all these dots are earthquakes, and here are the 4 injection wells, and there's lots of earthquakes right by the wells. And you can also see some earthquakes a pretty significant distance away. And so this is a 6-month time period. They then flowed the well back. So basically, they pulled all this water that they sucked out, and they brought the reservoir back to its native pressure, the pressure that it was at before it was perturbed by the oil and gas activity. And so now we're looking at a year, and you see almost no earthquakes. And there are, in fact, no earthquakes next to these wells. It's only at these significantly greater distances that you're seeing any earthquakes at all. And that again, is sort of a relic of the pressure changes that they weren't actually able to completely remove by flowing back this well. And so this was really clear demonstration to the scientific community that fluid pressure is really the responsible cause, is the cause for these earthquakes. By increasing fluid pressure, you're causing slip. And by returning your system to its native condition with its native fluid pressures, you really run out of earthquakes. So what is happening now? Oklahoma, in short, has more earthquakes than those of us in California. As a person that works in Oklahoma, I'm not sure if I should be proud or a little disappointed that we have so many earthquakes to work with. And the seismicity has really changed. There was very scattered seismicity prior to 2009. These are all the blue dots you see here. Whereas now we're looking at these red dots just in the past 6.5 years. So we're looking at very few areas that have many, many earthquakes. So let's just focus in on the Oklahoma seismicity very, very briefly. What we're looking at are accounts of magnitude 3 earthquakes every year. This is an average from 1978 to 99, so 1.5 a year. And you see in many of these years, there's actually no magnitude 3 earthquakes in Oklahoma. Not a single one. Sometimes there's up to 3 in 2002 and 2006. Something changes in 2009. There's 20, 43, 63. And you can see 585 last year. This slide is almost 3 weeks old, 4 weeks old. And there were 518 earthquakes. We're now at a 590 or 600 just in the last few weeks. So we've already exceeded the number of earthquakes that Oklahoma experienced all of last year, which was a record year, and we've still got 4 more months left in the year. So Oklahoma, the earthquake rate is just exponentially increasing. And you can see this is a count of the earthquakes that we're seeing in Oklahoma from late 2013 till June of this year, and you can see it's just continuing to rise and rise and rise. This earthquake rate is about 300 times higher than the sort of natural or historical rate. And we often see more magnitude 3 earthquakes in an individual day than we're seeing in years past, or even in a busy year past. We've seen 5, 10 magnitude 3s in an individual day, and there were certain years where we didn't have any. So it's dramatically different. There have also been 100 years worth of magnitude 4 earthquakes, so 13 in the past 6 months. So it's very, very busy. And the earthquake rate surpassed California in 2014. I don't know if we should be moving all of our resources to Tulsa. But what we're looking at here is just a count of earthquakes in Oklahoma. That's this darker line. This is a count of earthquakes in California, and you can see they shot ahead of us in 2014. So now I want to talk about one case study of seismicity where we've really actually been able to really get into the nitty-gritty and try to understand what's happening and model the physical processes. This I think, is one of the nicest studies I've seen of induced earthquakes. And this is some work looking at what's known as the Azle earthquake sequence. Azle's an exurb of Dallas. Here you can see Dallas here. This is where the earthquake sequence was. You're looking at 80 kilometers, so 50 or 60 miles away. There was a series of a few magnitude 3 earthquakes in late 2013 and early 2014. And so what we're looking at actually is a did you feel it map. And so people report in, probably anybody that's felt an earthquake. I hope you went to the USGS page to see what was going on. There's an opportunity for you to report your experience, and we make these maps to actually show what the shaking experience was of people. And so you can see the strongest shaking was close to this epicenter right here. Now, one of the big challenges for studying induced earthquakes is these earthquakes are occurring in areas where we don't typically have earthquakes. And so what that means is we don't have a lot of seismometers there. And so that means we don't get very good locations. We're not able to see small earthquakes. And so this is an example of what our initial locations looked like for this earthquake sequence. And you can see these are spread across about 10 or 15 miles. And this is just sort of using the standard USGS network that we have to locate earthquakes. But we fortunately actually had a temporary array. And now you can see that the earthquakes, instead of going from a scatter of 10 or 15 miles, we're looking at a scatter of a mile maybe. And so this is really showing you the effect of having more and better seismic data, as we can really identify what is happening in an individual area. So here we can see what the situation looks like. All these dots are showing you the earthquakes. The colors indicate the timing. And there were a number of ways that people were considering how these earthquakes could have been caused. They could be natural. They could be caused, there's a big lake right here. They could be caused by fluid injection. They could be caused by a production well. And so the authors of this study really went through an exhaustive attempt to try to understand what was going on. And so they said, are these earthquakes natural? Are these earthquakes being caused by lake level changes in this Eagle Mountain Lake? These earthquakes were occurring during a period of drought in Texas, and so the levels of this lake were at an all-time low. So that was a possibility. And the drought also meant that the water table had declined. Was this possibly a contributor? Obviously, there's going to be a lot of oil production and gas production in this area, and wastewater disposal is occurring in the area. So all of these different parameters needed to be consulted as to determine whether or not these earthquakes were induced. So first, they looked at whether or not lake level changes and water table changes would be able to affect the earthquakes. And so this is just a record showing you the lake level as a function of time from 2008 to 2014. And so you can see it's at an all-time low at the time of these earthquakes, but it's not dramatically lower than what we saw in late 2011. So a little bit unlikely, but they still computed the stress changes, what the effect of this lower lake level would be. And so you can see this yellowed area are the areas that are going to have stress changes associated with lowering that lake level. And you can see all these earthquakes shown here in black. They're really in an area that's unaffected by the lake level changes. So we can rule out the lake level changes. We can rule out the drought as being a source of these earthquakes. So the next question is it oil production? And so here's a lake on this map. All of these pentagons and lines are showing you individual wells and their trajectories. So you can see there's a lot of wells here. And so this blue is showing you the lake, and here's the lake here on this map. Here's our seismicity, which would lie sort of around here. So there's a lot of production wells that could be contributing. And there's also a couple of wastewater disposal wells that are high rate. So they modeled the situation to try to understand what the effect of the production wells and what the effect of these disposal wells were. And so you can see in 2009, the injection wells had not yet been turned on, but you can see all these blue little dots are showing you locations of oil or brine production. And so there's some small changes. 2009, 2010, the first injection well has been turned on. You start seeing much larger stress changes. 2011, the second one has been turned on. And 2013, you can see, depending on the parameters that you use, this is sort of what the stress conditions look like at the time of these earthquakes. And so this, again, is a combination of the effects of the injection as well as the production. And you can see most of these earthquakes are really lying sort of in these yellow to red areas of these stress changes. And so it really looks like it was a combined effect of the oil and gas production as well as the disposal of these fluids at depth that caused these. And another way to look at this is this is a look showing us time from January to early 2014, and these vertical bars are showing us earthquakes, and the wavy lines here are showing you the stress changes in the area of these earthquakes depending on the parameters that you use. And what you can see is that for most of these earthquakes are really occurring at the time of the largest change in stress, the largest change in conditions. So we're seeing not only a connection in space, but we're also seeing a connection in time. These earthquakes are happening sort of when we would expect them to, when the effects are at their largest. Now, I should probably bring this a little bit closer to home. You're probably asking me, well, Justin, are there induced earthquakes in California? Oh, yeah, we got them. We've got pretty much every kind of induced earthquake you could want, I guess, if you would want induced earthquakes. Most closest to us is the Geysers geothermal field that is just north of the Napa Valley. This is a photo of the Geysers geothermal field, and so these are where the earthquakes are occurring. So these earthquakes, we believe, are being caused by sort of the circulation of water that's being used by this geothermal plant. We've got groundwater withdrawal in the Central Valley that's believed to be responsible for inducing earthquakes. In fact, the very first, as far as we know, felt earthquake associated with hydraulic fracturing happened in the Santa Maria Basin in the 1980s. There's, we believe, some wastewater disposal-related earthquakes in the Kern County area, mining-related earthquakes in Lompoc, enhanced oil recovery in the LA Basin, as well as oil production. So we've pretty much got it all. Lucky us. But I would really say, we really haven't seen particularly large earthquakes associated that appear to be injection-induced. And I should actually point out there's a study that just came out a couple of months ago by some colleagues in our Pasadena office, as well as Caltech, who studied the past century of seismicity in the LA area and oil and gas operations. They really weren't able to see a very significant effect of oil and gas operations and earthquakes in the area. And so that's a pretty interesting finding. You might actually expect that since we're in a seismogenic area, we would see more induced earthquakes, not less, and we really don't seem to be seeing that. Now, the other thing that people are probably thinking about is, well, what about the Monterey Shale? We heard a lot about the Monterey Shale being, the savior for the U.S. This was going to be the biggest oil and gas reservoir that we've got. And then about a year or two ago, the Energy Information Agency released a report that cut the assessment of the possible production by 96%. So not so sure it's such a good opportunity. But this is actually, the Monterey Shale has been produced for over 100 years. This is somewhere that's been active for a very long time, but it's never been felt to be very economical. And so this is why it really hasn't been produced. It's hard to drill into, for one part. And there's also a very high percentage of produced water. This is a very water-rich environment. And so if this were suddenly to become economical, we'd have a whole lot of water that we would need to be getting rid of. But sort of based on what the EIA said, this seems fairly improbable. And I should also point out, California passed some of the first legislation regulating fluid injection causing earthquakes. And this was California Senate Bill 4 in 2013. And so California has actually sort of kept this in mind, kept the Monterey Shale in mind, kept induced seismicity in mind when considering induced earthquakes. So just as an outlook, I've sort of taken you through a bit of a tour of induced earthquakes, but as I showed you, Oklahoma's earthquakes are still continuing to skyrocket. What are we going to do about it? What can we do about it? Well, in some sense, I think we can control earthquakes at least to some degree. The experiment that these gentlemen and Jack Bredehoff did in the Rangeley field, really showed that we can sort of turn earthquakes on and off. And so this, is somewhat hopeful that we can at least mitigate the likelihood of larger earthquakes. We've also witnessed forced shutdowns of wells. A number of states have taken action and forced wells to be shut down in response to seismicity. And the seismicity oftentimes turns off. If you look at Youngstown, Ohio, Anthony, Kansas, Greeley, Colorado, the Montney Trend in Alberta, and Love County, Oklahoma, all of these areas have required either shutdowns or dramatic reductions in injection, and they've all seen reductions or termination of the seismicity. So action by regulators does appear to have some effect. Now, a number of states are starting to think about this. There are, in fact, 7 states that have either considered regulations or have actually passed regulations. There's this network of 5 states here: Colorado, Kansas, Oklahoma, Arkansas, and Texas, all of which who have seen injection-induced earthquakes, have all considered or have, in fact, taken action to regulate induced earthquakes. Ohio and California have also taken action to to try to mitigate the likelihood of large induced earthquakes. Now, the EPA actually sets base standards for regulations, but many states have taken this on their own. And the EPA has not yet put standards in that require regulation based on seismicity, but they have put out a report earlier this year providing guidance for regulators and operators on how to minimize induced earthquakes. So we're moving in the right direction. Those of at the USGS are also considering this problem. You know, we want to provide information to help reduce the likelihood of these earthquakes, or at least give people an idea of what the likelihood of being exposed to strong shaking or being exposed to induced earthquakes is. And so this is just a report that we released in April of this year, sort of showing preliminary results of our work on this. And so here, this is just a map showing sort of a first effort at what these assessments look like. And instead of projecting the hazard in a 50-year time frame, which is what we do normally for tectonic earthquakes, we're now looking at hazard in a one-year perspective. And so if we don't include the earthquakes we believe to be induced, this is what the hazard looks like in Oklahoma and Texas. And if we put them in, well, you can see it's a whole other kettle of fish. There's a big black spot throughout central Oklahoma. So it's pretty different. So moving forward, you know, I think there's some hope. You know, high earthquake rates are continuing, but you know, this may or may not be manageable. We've been fortunate in that we have not yet seen a large earthquake. There's certainly debate within the scientific community as to how large these earthquakes can get. You know, 5.6 is the largest we've seen, but you know, until August 2011, the largest we'd seen was a 4.9, and then in August 23rd, we had a 5.3. 3 months later, in November, we had a 5.6. So it's hard to say that this won't increase into the future. We also need to consider that these earthquakes are potentially more dangerous in the central U.S. Construction standards, construction regulations are not the same as we have here in California, so weaker shaking may be dangerous. Now, I do think that there's a lot of hope. There's been a lot of collaboration and cooperation between government, university, industry scientists, and regulators tackling this problem. This is a societal issue that we're all intent on working on, and I really do feel that, you know, in general, people are coming to the table in good faith. But it really requires data sharing and additionally more research. A lot of times, industry can be a little cautious as far as sharing some of their data, and they obviously are going to understand what's happening in their fields probably better than we do, because they're the ones working in these fields day in, day out. We have the expertise when it comes to earthquakes. They have the expertise to what is actually happening in their fields. But this is a field that is really hot and heavy. This is moving very, very quickly. There's lots and lots of research coming out pretty much every day. It takes pretty much all of my time just to keep up to date on what is happening. And I just wanted to show you just a few of the publications that have come out just in the last few months. 2 different seismological journals have released special issues on induced earthquakes, both actually, I believe, in June, Seismological Research Letters and The Leading Edge. Both of these special issues had a number of contributions from USGS authors. There was also a paper that just came out in Science in the last couple months that addressed induced seismicity instead of on a case-by-case basis, which is typically what is done. This really took a completely different approach and looked at seismicity, induced seismicity on the whole, and tried to address it as a nationwide problem and came to some very interesting conclusions. I also want to mention in the back there are copies of, well, there were copies of, it looks like everybody grabbed them, a review paper that sort of discusses the issues that I've talked about today at length. And if you want a copy and did not find one or there are none left, you can go to our website here. We have all of our publications available there. And we also update this pretty regularly with the latest information on what's going on with our research and, in general, our understanding of induced earthquakes. So I encourage you to take a look at that site as well. And I'll leave it there, and I'll be happy to take any questions that you have.
Well, thank you, Justin. Very informative talk, and I'm sure that he would be happy to answer any questions that we have. We've got one right here.
To your knowledge, has anyone that suffered damage in one of those earthquakes sued any of the injectors?
Yes, there are lawsuits that are pending. The Oklahoma Supreme Court just in the last month or so actually did rule that people who suffer damage can sue the oil companies. So this is something that is occurring in a number of states.
In Oklahoma, in that place where most of the induced earthquakes have occurred, it seems to still be going up. Is that what is the relationship to what they are doing there that keeps these going up, and how far much further will it go?
Well, I certainly don't know how much further it's going to go. Obviously, this is really dependent on what the oil and gas operators are doing. If they continue producing, most of these earthquakes are occurring in areas that have very large percentages of produced water. And as long as that is economical, they're going to have lots and lots of fluid that they need to inject. And so, it's your best guess to determine, how much longer it's going to go on. I should say Oklahoma very recently did pass some new regulations for part of the state to limit injection, and we've yet to see what the effect of that is. But
does the induced water continuing to rise, or is it steady?
Is the quantity of water, as far as I know, the quantity of water is still increasing. In general, due to the price of oil, there aren't a whole lot of rigs out there right now. There's not a lot of new wells being drilled, but any well that's been drilled, they're going to be using and pulling out.
I think you mentioned something about wastewater, and I was wondering also that it was salty, and I was wondering how water containing salt would penetrate from the oceans into Oklahoma.
Well, so these are ancient oceans. These are relict oceans, and that's sort of how the oil forms. It's coming from the same place. It's not penetrating. It was there to begin with.
One of the slides that you had was interesting to me. It was the train with all the load of fresh water that's taken. Now, fresh water is one of our most precious resources, and yet you're putting that water down in the ground and contaminating it. It's no longer fresh water. Most of it can't be used. What is the issue here, and why can't we use salt water in fracking?
Why can't we use salt water in fracking? Now you're pushing the limits of my knowledge of the oil and gas industry, but typically you want to use fresh water because salt water is actually pretty bad for the wells, and the fresh water, I believe, will actually break up the rocks a little bit better. But this is really pushing the extent of my knowledge. So.
I think the thing is that there's already salt water down there, and if you add salt water to it, it can't be that difficult. Now, there must be something about the chemistry of the fresh water versus salt water that's important to the oil industry, and they can't seem to cope with it or don't care if they use up all of our fresh water.
They wouldn't be using the fresh water if they didn't have to, because fresh water is expensive, and oil and gas, they're there to make money. They don't do anything if it's not the cheapest solution.
Back here. I thought it was really impressive, the magnitude of the Alberta quakes. And I wonder what ideas there are about the difference between Alberta and Oklahoma, and whether there might be faults that are just potentially more susceptible to larger quakes.
It's a really good question. Certainly we've seen larger induced earthquakes in Oklahoma than we have in Alberta, but the frac-induced earthquakes are indeed larger in Alberta. My best guess, this is really an area of active research. I've spoken with a number of Canadian colleagues about this, and my best guess is it seems that frac jobs in Canada are often much bigger than ones that are done here in the United States. This production area, the Montney Trend, is really out in the middle of nowhere. There's pretty much nobody out there. There's the drillers and probably some moose, and so that may be part of why these are bigger jobs, is that there's just less people to bother. But yeah, I'm really not sure. This is something that we're still working on.
We're are the oil and gas companies required to do an environmental impact report before they did any of this, or is there no regulation whatsoever?
No, there is a permitting process as far as drilling oil and gas wells, or for injection wells. Like I mentioned, the EPA sort of sets base standards, and those base standards do not include earthquakes. And in fact, the EPA has this regulatory authority from the Clean Drinking Water Act, which says nothing about earthquakes. And so you'd have to come up with a way to sort of say that earthquakes could affect the safe drinking water for them to really have a legal reason to be able to regulate that. Now, a number of states, as I mentioned, are starting to regulate based on seismicity, but this is an evolving field. It's really been the states that have witnessed these big changes in earthquake rates that are starting to do something about it.
So this is based on a childhood memory of visiting Ponca City, Oklahoma, where there were oil wells all over the place. And I remember as a child going down to play in the creek, and it was full of oil. Is that what used to happen with this wastewater? Did they just let it go on the surface of the earth before they started injecting it? What did they used to do before they injected it?
Well, they've been injecting wastewater for a very, very long time. I can't comment specifically to what was happening in Ponca City, but wastewater injection has been going on for a very, very long time. I think really the big difference that we're seeing in northern Oklahoma and southern Kansas is a change in practices that is resulting in higher volumes of this produced water. And so that's probably the biggest change. And we're also injecting in new places. There really wasn't a whole lot of injection in northern Oklahoma before. And so having more water and going into new areas, I think, are really sort of why we're seeing this big increase.
Do 100% of them drill injection wells? Do any of them take this produced water and filter it or clean it and then distribute it over a large amount of surface area? This way they're not causing this, even at a higher price? And does this technology exist?
Yeah, it's really dependent upon the field. It's dependent upon the landowner. It's dependent upon the operator. Generally, drilling these wells is very expensive. A disposal well is probably on the order of $2 million. Oil companies are in business. They're not going to do anything that they don't have to do. So if they're able to clean the water and discharge it on the surface, either for agricultural purposes or they're able to put it into a creek, stream, lake, they're going to do it. For example, in the Raton Basin, on the Colorado side of the basin, only about 30% of the wastewater is actually injected and 70% is discharged on the surface. So it's really dependent on where you are. If you go to the New Mexico side, all of that land is actually the Ted Turner Ranch, and they are required to inject all of it. And so this is where you see the landowner is taking effect. So it's really it depends on where you are, but oil companies are in business. They're going to use the cheapest solution.
It is my understanding that there are several water storage districts in the southern end of the Central Valley. The semi-tropic water storage district is the one I worked with for several years, and there was no mention of any earthquake effects for when they actually pumped water from the aqueduct into the underground aquifer, and there was no concern about earthquakes.
Okay. I don't know much about what was happening there. If I were to hazard a guess, it's probably significantly smaller volumes than what we're looking at these wastewater injection wells that are much bigger. And also, you're going to be injecting typically sort of into the groundwater aquifer. And when you're in the groundwater aquifer, you're probably not going to have communication to the depths where you have faults. Mm-hmm. You need to be in competent hard rock to produce earthquakes. And this is really going to be in a soft sediment strata, so there's not going to be the transfer of this fluid pressure to greater depth.
To bring this much closer to home, there's both fracking and injection wells in the southern part of Santa Clara County. And has anybody been monitoring what's going on there? And given the amount of major faults around here. Is that likely to make any difference if they're doing that kind of disposal of water here?
Well, I wouldn't say that there's any additional monitoring activity that's going on specifically for this area. You know, obviously, the Santa Clara Valley, the whole Bay Area is instrumented very well. So if we saw a significant change in the seismicity, you know, alarm bells would be raised. You know, as I mentioned, there is regulation now in California that isn't fully in place as far as fracking and seismicity, but there is no specific regulation on wastewater injection and seismicity in California. So it's still an evolving situation, but we have not yet seen anything.
Are we seeing any deniers, any science deniers on this? Any politicians claiming I'm not a seismologist and the jury's still out?
I don't encounter that too frequently. There are some companies that deny that there are induced earthquakes. Certainly some companies deny that they induced earthquakes. But it's very infrequent that I hear people denying the existence of induced earthquakes entirely.
Great. Well, maybe on that note, we should all thank Justin, and thank you again all for coming. And if any of you still have burning questions, I'm sure Justin will be happy to answer them, so please feel free to come up. So thank you again.
Hi.